working. I'll turn it in right now.
Okay. Right. What's up, you guys? Hopefully you're doing all right. I know one of you just got out of a couple of you actually just got out of a stat test. Hopefully you're feeling okay after that. Let's get through this worksheet today. Hopefully some of you have had some time to look at it at least. We want to work through these problems here and see what we can do. So the first problem here says show that if lambda and mu are invariants, i.e. scalars, Si and Ti are contravariant components of a vector field, so different vector fields S and T. The vector components defined by lambda Si plus mu Ti are also contravariant. So let's look at, we'll call it Pi equals lambda Si plus mu Ti. And so we'll look at Pi prime. And that would be lambda Si prime plus mu Ti prime. And now what do we know? We know S is a contravariant component, so that's partial Xi prime. I'll write partial XR, SR plus mu, and I'll use the same letters, partial Xi prime, partial XR, TR. And now I can factor that out. I can say partial Xi prime, partial XR, and then lambda SR plus mu TR. And now that's partial Xi prime, partial XR, PR, which is a 1-0 transformation. So does that kind of make sense? Maybe a little bit, hopefully. Look at the next problem here. See, we have S11 is y squared, S12 is xy, S21 is x squared, and S22 is y. Also, let's see, T1 down is going to be square root of xy, and T2 down is going to be xy. It says compute the outer product Sij Tk by specifying the 8 components individually. So S11 T1 be equal to, basically take the 1 component, multiply it by the 1 component, you get x, or square root of xy, y squared. You could write that as square root of x times y to the 5 halves. S12 T1, well, let's see, S11 T2, S11 T2 be xy times square root of xy, so xy square root of xy be equal to xy to the 3 halves. And S12 T1 be xy square root of xy, which would be equal to xy to the 3 halves. S12 T2 equal to xy, hold up, this one's wrong, T1, or sorry, this one was wrong. S11 T2 should have been xy times xy, which would be x squared, y squared, sorry. Now S1, 2, I'm sorry, it's not. It should have been y squared times xy, which would have been xy cubed. And then S1, 2, T2 should be xy times xy, should be x squared y squared. And then S21, T1 will be x squared times square root of xy, should be x to the 5 halves, square root of y. S21, T2 would have been x squared times xy be equal to x cubed y. S22, T1 be equal to y times square root of xy be xy to the 3 halves. Or sorry, square root of x times y to the 3 halves, and then S22, T2 will be xy times y, which would be xy squared. So those are the 8 components of this outer product. And if you want to call them like maybe P11 up, 1 down, P11, 2, P12, 1, P122, P211, P212, P221, P222. And so it's 8 components for our tensor. So any questions so far? It's the outer product. Basically just creating a tensor of higher order by multiplying every component of the first tensor by every component of the second tensor. That creates a tensor of higher rank. In this case, creates a 3-dimensional tensor, or a rank 3 tensor. 3 indices, 2 up and 1 down. This one says, prove that if G, which is Gij down, is a covariant tensor of order 2, and U, which is Ui up, and V, which is Vi up, or Vj up, are contravariant vectors, then the double inner product GUV is an invariant. So let's look at that. Let's look at G I prime J prime U I prime V J prime. Since all of those are tensors, we can use the tensor transformations for each one. So what we're going to do is we're going to do partial x I prime, partial x r, partial x, whoops, those should be swapped for the J, or for the G, sorry. Partial x r, partial x J I prime, partial x s, partial x j prime, g r s, and then partial x I prime, partial x k, u k, partial x j prime, partial x m, v m. And now we can rearrange some of these. Oh, this should be a prime. And so now we can rearrange these two, can give me a delta rk. And these two can give me a delta SM. And then I can leave it GRS, UK, VM. And now use the deltas to change, I guess we'll change K to R. So we'll call it GRS, UR. V will change that M to an S, which implies invariant. Basically, since no more partials. So yeah, that's an invariant. does not depend on the coordinate system anymore. The Jacobian basically is no longer in the equation because all of those turn into deltas. That means it's invariant. You compute it in one, it's the same scalar that you get regardless of coordinate system. So, cool. Questions? All right, let's see. Another one. How many tensors can be created through contraction? Well, I have 3 options up and 2 options down, so each of the 3 up can be contracted. With either of the 2 down. So 3 times 2, which is 6 contractions. So I'll just take a minute, pause, see if there's anything that you want to talk about. Any questions so far before we finish up? One more problem here. I think this worksheet's actually one of the easiest worksheets we've gone over so far if everything has been making sense. There's not a whole lot to this worksheet, or this section in general, really. I mean, conceptually it's pretty deep, but you know, on the surface, just doing the computation, it's not bad. If everything else made sense. So let's look at this last one here. It says how many potentially different tensors of order 2 can be defined by taking the outer product of Sijk and Tijk, and then contracting twice. That should be then contracting twice. So it's probably best to relabel this thing as like TRSP or something like that. And so then the outer product would be something like Sijk TRSP or PQR or something like that. Let's call it PQR. PQR. That creates, ooh, this one's pretty gross actually. So this one's actually really complicated. This will become something like, I don't know, we'll call it U, IJP, KQR. So that's the outer product. So we got the outer product, now we can contract twice. So contract this twice. So for the first index, I can pick any one of these 3, and it has 3 options. So 3 times 3 is 9. 3 times 3 for the first contraction. So 9 possibilities for the first contraction. 9 possible contractions. Now, once we do that, we'll get something that only has 2 indices up. So after one contraction, so after the first contraction, there will be 2 up and 2 down, which is 4 for the second contraction. So 36 total possible contractions. Does that make sense? That one's probably the sneakiest little problem. Really, that's just a combinatorics problem. So just throwing in some different types of math just to spice it up a little bit, because don't want you to get bored with all this fun calculus stuff. Any questions? Only took about 15, 16 minutes, so that was good. Yeah. Cool. Well, if there are no questions, you guys are free to go. I'll stay in touch. We have chapter 5 coming up on Wednesday, and so we get into some real deal tensor stuff. So we've got all the notation down. We know what they are, but now we need to see some real examples other than the Kronecker delta and the tangent vector and the gradient. So we'll get another new tensor, a real tensor, something that there is like you can actually work with and kind of understand what it does. So that's coming up on Wednesday, called the metric tensor. So if you want to preview the section, go for it. It's chapter 5 in our outline or our textbook. Anyway, you guys have a good afternoon, and I'll talk to you later. Oh, sorry, Andrew. I'll catch up on the Discord.